Hello and welcome to my channel. I am the Mad Computer Scientist. We are getting close to 100 subscribers on this channel, so if you are new here, I'd like you to do me a favor. Please hit that like button, of course, but also be sure to ring that notification bell when you hit the subscribe button. Thank you. On this channel, we discuss math, computer science, and tech topics that are of interest to me. Today we're going to discuss the binary numbering system and bitwise operators. Why are we discussing bitwise operators? Because bitwise operators allow us to take some interesting shortcuts when programming, and of course, you might have guessed that I do love computer programming. Let's get into it. And I'm sorry for those who came here after the Terrence Howard video, but this will not be that entertaining. I will try to make it more entertaining, though. I am sorry we will not be doing anything as exciting as using the wave conjugations to prove that Pythagoras shot JFK from the grassy knoll. If you know what that means, please let me know. We're going to talk about something even more exciting, base numbering systems, and I can feel your excitement from here. As you probably all know, we use base 10, which contains the digits 0 through 9. In base 10, each position is 10 times more than the previous position. Other numbering systems also exist. We have Roman numerals, which is non-positional, hexadecimal, which is base 16, octal, which is base 8, and the Babylonians used a base 60 system. Now, if you've dealt with binary and are thinking it's hard to deal with, you're probably wondering why we don't make computers using base 10. After all, it would make it easier for us, at least when we're doing math outside of the computer. And there is a good reason for this. The problem is we would need a lot more components to make base 10 computers. To cut down on costs, we use binary. In fact, Leibniz was one of the first people to propose a binary system of arithmetic in 1703. And if you're a scholar of STEM history, you might also want to know that Charles Babbage actually did intend to make the analytical engine as a base 10 system. Fortunately, the analytical engine was never built. Perhaps, since he did know George Boole, and obviously, as a mathematician, was familiar with Leibniz, if he had done this, he might have managed to build both the difference engine and the analytical engine, but we will never know. Now that we have discussed different positional numbering systems, let's go on to what this video is about, base 2. Now, when you use positional numbering systems other than base 10, you usually say a number like this, 1, 0, base 2, rather than saying 10, because that way people don't get confused and assume you're talking about the decimal number 10. Now, you probably already know the basics of this, so I encourage you to skip ahead. Binary does have only 2 digits, which are 1 and 0. Each position is double the previous one, and counting in binary would sound something like this. 0 base 2, 1 base 2, 1 0 base 2, 1 1 base 2, and so on. Now the reason for using binary, at least as a programmer, is because it allows us to do bitwise operations fairly easily. Now when we write binary, we usually break it down into groups of 4, such as 1 0 0 0, 1 0 1 1. The reason for doing this is because the systems octal and hexadecimal were used as a shortcut because it's fairly trivial to convert from other numbering systems that use a power of 2 to binary. The good news is I'm not going to spend too much time on this slide because binary operations are the same for basic arithmetic mostly as they are for any other base system. Just remember that if you add 1 times 1, you need to carry the 1. Using the binary numbering system allows us to do Boolean algebra fairly easily using the bitwise operators. Several operations in Boolean algebra are OR, AND, NOT, and XOR. If you've studied electronics, you may also do NOR and XNOR. And what we are going to have to go over here is something delightfully known as a truth table. What you see on the bottom of the screen is the truth table for the bitwise OR. If you have 1 and 0, you get 1. If you have 1 and 1, you get 1. If you have 0 and 1, you get 1. The only way to get a 0 from a bitwise OR, which is the inclusive OR by the way, is to have both 0 and 0. Are you still with me? I wouldn't blame you if you were not, because you might have felt like I just insulted your intelligence, because this is easy. I assure you, it is. Now, truth tables do get more complicated when you do multiple operations on them, but we're not going to do that in this video. Next, we have the exclusive OR. It's similar to the inclusive OR, but we only get a 1 when we have one bit that is 1 and another bit that is 0, as you can see from the truth table. A 0 and a 0, or a 1 and a 1, will result in 0. And by the way, 1 equates to true usually, and 0 equates to false. If you felt like the previous slides insulted your intelligence, I'm afraid this one won't be any different, because we're going to go over the bitwise NOT. Now, NOT is simple, we're just flipping a bit. If we have a 0, we get a 1, and if we have a 1, we get a 0. And finally, we're going to go over the bitwise and the only way we can get a 1 out of a bitwise AND is if both of the positions in the binary digit are 1. So the good news for everyone who failed a first grade math test by getting this one wrong is that in Boolean algebra at least, 1 and 1 is 1. Now let's go on to what we can do with all of this. If you have stuck with me this far, I would like to thank you because I know you probably feel I have greatly insulted your intelligence given how easy the last slides were. But if you've studied electronics, you know why all of this has practical applications, and it also allows us to do several neat programming tricks. One of my favorite programming tricks is to use the bitwise XOR to swap two integer variables. Normally, to swap the values of two variables, you need 3 variables, but we can save memory as long as we're using integers. You can also quickly determine if a number is a power of 2. Just take an and bitwise AND it with n minus 1. If the result is 0, it's a power of 2. You can use a similar trick to raise a power of 2 to the next power of 2, where you do an XOR on n and that number minus 1. Then you add 1 to it. However, there is an easier way to do that if the number is already a power of 2, and that's that you simply shift left, which is a command used in many programming languages that provides a quick way to multiply by 2. There is a similar command called shift right, which gives you a quick way to divide by 2. Now, it's similar to multiplying or dividing by 10 in decimal, and it would pretty much work the same way for all positional numbering systems. Thank you for watching. I do appreciate your support. If you have any idea for future videos, please leave a comment down below. And as long as I am able to, I will continue to respond to all comments in some way. Also, remember to like, comment, and subscribe.